Hi people, welcome back to the next lesson on stress and strain. I worked out 3 quick examples in the previous lesson. Let's look at a few more. It says determine the increase in length of a steel tie rod 3 meters long and 30 millimeters diameter when subjected to a tensile load of 120 kilonewtons. They were given the E value. Okay. Now remember, stress is equal to force over area and strain is equal to the changing length over the original length. Okay. Right, what does it want us to determine? It wants us to determine delta L. Okay. That's what it wants us to determine. This here, it wants to determine delta L. Okay. And that there is L in the formula. And from this, we are going to get the area, okay? That's F that's given, and of course, that's E that's given, okay? So, delta L. So, there, we must determine delta L. They've given us L. We can work at the area. We've been given F, the load acting, have been given E, right? And I said determine delta L, and I said there, right, what's delta L? Delta L. Delta L is equal to the force acting multiplied by the load over the cross-sectional area times E. And that's it. There's the formula. Plug in the values, get the answer. Right, let's see. Right, the load is 120,000 Newton. You need to convert to newtons multiplied by L. L is 3 meters converted to, if you get, a lot of people make the mistake, people, I'm saying it over and over, that will be 3,000. Convert all areas distance to millimeters over the cross-section area, which is quarter pi times diameter squared, which is 30 millimeters squared. If you leave that as 3 and you make the 30 millimeters, it's going to be wrong. I'll say that again. If you leave that as 3 and you make the 30 millimeters, it's going to be wrong. You'll get the right numbers, but the decimal will be in the wrong place. Times E. Now, very careful. Do you see that K there? Do you see that K there? Very careful. It's 205,000 Newton per millimeter squared. 205,000 Newtons per millimeter squared. If you don't put in the 1,000, it's going to be wrong. Right. Do the calculation and see that you get the same answer that I do. And what did you get? And remember, if you cast your mind back to what I said, you can't get a big number. You can't get a big number. If you get a big number, you've made a mistake. And the answer is 2.48. And because it's a length, it is millimeters. That's it. Okay. So when we have a tie bar, steel tie bar, of that length, of that diameter, you can see it's very much longer than it is across its section, and it is loaded to a load of 120,000 newtons, and it has an E value of that there. It will stretch by an amount of about 2.48 millimeters. If you get a big number, you made a mistake. Okay. Right, people, let me clean up the board and let's do another example. Right, people, next example there, a timber specimen. Normally we call it a specimen when you take like a piece of material and you subject it to forces or whatever in a machine and you study it. We call that a specimen. A timber specimen of 50 millimeter square cross section was initially that length. Right, let's see what it's giving us. It is, from there we can work at the area, was initially, and that is L, parallel to the grain. After an axial compressive load, we're squeezing it. That's F is given us there. What is this about? It says it's given a load of that, which is F, was applied, the specimen shortened by, so they're also giving us delta L. Determine the longitudinal elastic modulus for the timber. That means find E. That's the question. Find E. Okay. Right. What's E equal to? E is equal to stress over strain. Can we find stress? Yes, stress is equal to force over area, so we can find that. Right, and then it says what's strain equal to? Strain is equal to delta L over L. Yes, we can find this, we can find that. We put it into the equation, job done. Okay, so we know there that E is equal to FL over A times, it's delta L. Okay, what's F? F is 40,000 newtons multiplied by the length as millimeters, so we can use it as it is, which is very nice. Don't need to change anything. That nasty line, eh? The area, what's the area? It's 50. Now a lot of students just make it 50 millimeters square. No, it's 50 millimeters by 50 millimeters. It's a square section, so it's 50 millimeters by 50 millimeters. Okay, a lot of people think it's 50 square. No, it's 50 times 50. Right, multiplied by the changing length, and notice there it's a small value, 0.29. Right, work at the answer and check that we get the same answers. Right, the answer I get is 1103. Let's see, 11034. 11034.48. And what's the units of measurement for E? It's the same as stress. So it's newtons per millimeter squared. And if you want to be really fancy, you can divide it by 1,000 and write it like so. Kilo newtons per millimeter squared, if you're feeling really in a fancy mood. Okay, but that answer and that answer is both correct. But if you write it as 11.034 kilonewtons, sorry, if you write this answer as 11.034 Newton per millimeter squared, it will be wrong. Okay, so it's either 11,034.48 Newton per millimeter squared or 11.034 kilonewton per millimeter squared. Okay, people, so you can see there we were given the load, the original length, the cross-section area, by how much it's shortened under compression. We were able to work out Young's modulus for that particular timber. Okay, right, let's clean up the board and do another example. Right, people, the next example, a mass concrete pier. What is mass concrete? Normally mass concrete is like dam walls, okay, where we build like lots of formwork and we chuck in loads of concrete, lots and lots, okay, to turn like into, and just make it one massive heavy lump of concrete. Okay, that's mass concrete. A mass concrete pier of rectangular cross section, 600 by 100 by 800 and 2.2 meters high. Notice millimeters and meters, the units. Okay, is ringing bells, we can't mix them up. Long or high, that should be high I think actually, carries an axial compressive load of 2.5 times 10 to the power 6 newtons. Can you see that? Okay, determine number A, the stress in the concrete at the base of the pier, the amount of shortening that will occur in the pier. Okay, so let's see, it wants us to determine stress and I want to determine delta L. That's the question. Then it goes on to say the density of concrete is that over there. Now people, that's a standard figure. Okay, right, just something about density. What's density? Now density, there's a formula for density. We write it like so. That's the Greek word rho. Rho, R-H-O, but we don't read it as rho. When we in engineering, we write it as low. It's like a P with a little tail on, and I'm gonna call it C for concrete. Okay, and that there is 2,500 kilograms per cubic meter, as is given there, and the formula for density is equal to mass over volume. Okay, that is why density is measured in kilograms per cubic meter. So if we take the mass of something and divide it by its volume, we get the density of it. That is why that's kilograms per cubic meter. Okay, Young's modulus is given as 13,000 newtons per square millimeters. Can you see that? 13,000 newtons per millimeter squared. Now let me draw a quick sketch quickly. Right, let me see. Right, so it says it is 800 wide there by 600 that way by 2200 millimeters high. Okay, and it's undergoing a load of 2.5 times 10 to the power 6 newtons. Okay, and that's millimeters. Here we go. That's it in a picture. Right, Mr. Dada carries a load of that there. Determine the stress in the concrete. Now, it's given us this over here. Why do you think that? Because concrete has a weight. Okay, so what we're going to have to do, we're going to have to work out the weight of the concrete pier there, given that over there. Right, and when you work out the weight, we're actually turning the weight into a force, because weight is a force. Okay, and once we got the weight of the concrete and the force acting, we can add the forces, we can add the weight to the force, and that will be equal to the total downward load acting on the pier. Okay, and once we got the cross-section area, if I did this, let me do this quickly here. Okay, there's my pier. So, and of course, this bit here, that bit there will be my cross-section area that's been acted upon by the total loads there. Okay, right, so let's work out the weight of the concrete first. So let me leave that as green. Yes. So I'll say weight of concrete. How are we going to do that? Okay, we got the density is so many kilograms per cubic meter. So what do I need to do? I need to work out the total volume of the concrete, which is 800 times 600 times the height of it. Okay, that will give us the total volume. And if I multiply this by the mass there, I will get the total mass of the concrete. How do I convert it to a weight? I multiply that by 9.81, and that will give so many newtons of concrete. Add it to F, that will be my total F acting for my formula. Right, so but remember here, density is given in kilograms per cubic meter. So I'm going to have to use the dimensions here in meters. So it will be 0.6 multiplied by 0.8 multiplied by 2.2. Okay, that will be the total volume of the concrete. And if I multiply that by 2500, that's the total volume multiplied by that there. And that, all of that there is the total mass of the concrete. But I want the weight. And I multiply it by 9.81. Work at the answer and see what you get. And check yours against mine. And the answer I get there is 25,898. 25,898.40 newtons. So therefore, I'll say force acting total is equal to 25,898 plus the load acting, okay, of 2.5 times 10 to the power 6 newtons is equal to, I'm going to add it here together. So I'm going to say plus 2.5 exponent 6 is equal to 2525. Right, people, so my total load due to the load acting given there and the weight of the concrete that's acting on the base there is 2525898 newtons. Okay, right, number A. Calculate the stress in the concrete at the base of the pier. What's the formula for stress? It is force over area. There we go. I give you a mark for that. Stress is equal to force over area. I'm going to squeeze it in here. Is 2525898. Now people, I said convert all to newtons and millimeters squared, so I'm going to say 600 times 800. And if I work it out, check my answer, get the same as me, I think I get 5.26 newtons per millimeter squared. Okay, so people there, so for a concrete column or pier of that dimensions, with that load acting, with that concrete of that density, okay, that will be the total stress at the base of the pier of 5.26 newtons per millimeter squared. Okay, are we done? No, it wants us to work out the amount of shortening that will occur in the pier. And what's the formula for shortening? Shortening is equal to it wants us to work at delta L. Okay, just think about it while I clean my board quickly, and we can work that out, and then we should be done. Right, people, I want us to work at the shortening. What's the formula for the shortening? Is delta L. Oh, sorry. Delta L is equal to the load acting multiplied by the original length over the total cross-section area times E. Right. So what's the total load? The total load was, let me check what the total load was again. People, the total load was 2525 was 2525 898, I think it was. Yep, 898 multiplied by the original length, which is 200 millimeters, over the cross-section area of the base, 600 by 800. Well, you could say it's 48 naught if you were really smart. No? That's 48 naught. And E, what's E? Yep, E is 13,000 newtons per millimeter squared. If you put in 13, it's going to be wrong. You can get the right numbers, but the decimal will be in the wrong place. Okay, and this thing will be 1,000 times too big. So it's 13,000 newtons per millimeter squared. And the answer must be in so many millimeters. Do we expect a big number or small number? We expect a small number because it's a shortening. Okay, so right, work the answer out and check your answer against my answer. And we got a nice small answer of 0.89 millimeters. There we go. Okay, if you got 89 millimeters, if you made that a 13, that would have been 890 something. That will be wrong. I mean, a member can't shorten by 890 millimeters, people. It can't. It's impossible. Unless we're on Venus or Pluto or Mars or on the Sun, but we're not. We're on planet Earth. Okay, so it's a small number, so that makes sense. So this column with this dimensions under that load, with that mass of concrete, density of concrete, and that E value will shorten by just under a millimeter under that load. Okay, people, that's all the examples I'm going to work at, and I'm going to quickly dig out the exercise I gave you, and I just want to say something about it quickly. Sorry, man, I didn't mean that. Anyway, people, this is also on Blackboard. There's an exercise I gave you. I just headed chapter 3. That's the first page there. The ones that's marked with these heavy little dots, you do those ones. So it's chapter 3, numbers 3 to 9, and 17 to 21. Okay, and if you go to the second page of the handout there's the answers. So for example, chapter 3, numbers 3 to 9. Okay, there's chapter 3, so that's 3.3 as answer to number 3, 4, 5, 6, 7, 8, 9. And if you do the other ones, number 17 to 21, you go to the answers. There's answer number 17, 124.3, 18, 19. I marked it out for you. Okay, so do those ones. Chapter 3, numbers 3 to 9, and numbers 17 to 21. And that's the answers that I marked for you on the next page. Okay, people, work through that, and then I'll see you in the next video.